Do we
Awesome.
anticipate more people joining, or can we start? Sparsh?
Yep. Hi, Ojus. Can you hear me?
Yeah, I can.
Okay, perfect. I think there was something going on in the background. No worries. Welcome back to another session at TestMu Conference 2026. I'm Sparsh KC, Developer Relations Manager at TestMu AI, and I will be the host of your session today. Before just we start in, a quick housekeeping item before we start the session. So you can drop all your questions in the Q&A panel, and we will be taking those questions at the end of the session. And the chat is open for conversations, and the session is being recorded, so it will be available on demand after the conference. So let us get started. I will introduce the session today that we are addressing. Most of us have never had to say out loud what cloud infrastructure assumes about our traffic. It assumes a new request whose cost you can estimate before it runs. Timeouts are seized against it. Capacity plans are forecast from it. Rate limits and billings are built on it. Agent workloads do not honor this assumption. An agent decides what work to do while is it executed, which means tool calls, model invocations, and retries are only settled once the run is finished. So the question this session asks is a sharp one. What happens when unpredictable work lands on the infrastructure designed for predictable requests? Here to answer this question is Ojus Save. Ojus is the developer relations engineer at Render, where he uh, develops application from code to production. He has spent close to a decade in developer-facing roles at Zender, Zoom, Google, and many more, working across engineering, product, technical education, and community. And his current focus is cloud platforms and AI infrastructure. In this session today, called Cloud Assumes, you know what a request will cost. Ojus will address all our questions about cloud infrastructure and AI agents. Hi, Ojus, how are you?
I'm good. Thank you so much for having me here.
Awesome. We are very much excited for your talk today. And this is a very interesting talk because I think this is a talk of the hour because AI agents can suck dry our cloud cost. So I think people are very eager to learn about how it can navigate this in this agentic era.
Yeah, cool. So yeah, thank you so much for having me here. And folks, all the folks who are attending, I would recommend you guys stay here till the end. I do have some credits for you guys. So, hopefully you guys are able to stay here till the end. Anyways, let's get started. So here is my take. Every piece of cloud infrastructure that you have ever used makes one assumption about your workload. And it makes that assumption before your code runs. It assumes that the code of a request is knowable at the moment the request arrives. You may size a timeout against it. You forecast a capacity from its average. You can rate limit on it. You bill by it. You can have four separate systems all resting on the same quiet belief that when a request shows up at the door, something about it tells you how much it is roughly going to cost. And that belief has held for as long as we have been putting things behind an HTTP endpoint. Surprise, agent workloads break it. And they break it right at the source. Hello, everyone. My name is Ojus Save, and I work on the developer relations team at Render. I spend most of my time watching people put things into production. Before Render, I was at Zoom, and before that, I was at Google. But production workloads is mostly where this talk is coming from. Over the next few minutes, I'm going to show you two runs of the same instruction and explain why one of them costs meaningfully more than the other. And I would make a case that nothing available to you at the start could have told you which one you were about to get. So, What do we see in this slide? I will say this slide shows you the whole problem in one picture. At the edge on the left is one request, one prompt, one HTTP call. Your load balancer counts this as one. Your rate limiter counts this as one. Your billing system counts this as one. However, inside the runtime, it is not one thing. It fans out a sequence of decisions, and those decisions get made during the execution rather than before it. The agent that you're using picks its next tool call based on what the last tool call returned. It could read a file. Maybe what's in the file determines whether it reads 3 more or none more. So you are left with a mismatch, and the mismatch is structural. The thing you count, the request, and the thing that spends money, the execution, are two different objects. You're billing one and you're consuming another. Again, this mismatch is the entire talk. Everything else I show you follows from it. I want to name a specific moment because the failure originates earlier than most people expect. You can call it the admission event. It is the instant your infrastructure accepts the request. At that instant, your infrastructure makes, say, 4 commitments. It could assign a timeout. It takes a slot in a worker pool. It could open a billing record. It could decrement a rate limit bucket. All 4 happen at the same millisecond, and all 4 rest on what system knows right then. So look at what it actually knows at that point. Your system probably knows that there is one prompt. The tasks are probably unknown. How much compute you require is probably unknown. And let me clarify what the word unknown means, because people tend to hear it as hard to estimate. Here's my take. It's not hard to estimate, but it is undefined. There is no number sitting somewhere that a smarter system could have looked up. The workload has not been discovered yet, and the only thing that it discovers is running it. Your infrastructure may have priced this run before the run existed. But then comes the cruel part. The request returns a 200. It looks great. Nothing in your monitoring will ever tell you a guess was made, and nothing in your invoice will tell you that which guess was wrong. Now, wherever you're setting, I'm going to make you commit a number in your mind, because this is where it is more interesting and where you are wrong on the record. Here is an instruction that I gave an agent. Investigate the incident, find the cause, fix it safely, deploy a preview, and verify the result. 5 instructions, nothing super exotic. I ran it twice, and both runs are recorded, which you will see in the next slide. So I don't know, do we have chat available? We have. I would like to ask you guys, think how many steps would show up in the graph. It could be 4, it could be 10, it could be 20. Don't overthink it. Just look at these 5 instructions that I've put and guess how many steps would it require for that run. Okay, I'm going to give you guys a couple of seconds before you put some numbers in the chat. Okay, someone said 20. 25. More than 20. 100. All right. Um, I think we have enough number of guesses. So again, hold on for your number. We will come back for it with the real one in about maybe like 4-ish minutes. Again, this is the prompt that I used. Investigate why checkout latency spiked after the last deploy and ship a safe fix. This was done on Tuesday, and I guess most of the people who are working with agents in production are using some of this. This is run number 1. I'm going to call it the clean path. Here is what happens. The agent is going to investigate it, form a hypothesis, patch, verify, return the summary. This comes to 5 nodes. The first hypothesis happened to be correct and the test happened to pass. So there was nothing to reconsider and the agent did not reconsider anything. As I said, this is the clean path. It is a good run. It is also the one that typically, if you are demoing something, this would end up in your demo. And it would also end up in your capacity model and whatever spreadsheet somebody used to price the product. This is the run that you would typically design for. Now, here's the funny part. This is run number 2, same prompt, same repository, and same agent. Investigate, hypothesize, patch. However, this time the test fails. So the agent goes back, patches an edge case that it thinks it has no way of knowing until about the failing test surface. It verifies the second time and then it returns. This time it's 7 nodes instead of 5. Now, I want to be careful about how we read that because the instinct is to the file as the error case. This is a completely successful run. Your agent encountered an evidence, responded to it, and this is exactly the behavior that you want. It found more work because there was more work to find. Again, nobody in this trace did anything wrong, but this run will still cost you more. Let's look at these 2 requests side by side. In the clean path, we have 5 nodes, and in the disrupted path, we have 7 nodes. So if you thought like, hey, 5 was the right number, and you were still right, but I also don't want you to walk away with 7 because node count is misleading. And the way it misleads is the part that we should all care about. Let's look at what these 2 extra nodes are. One of them is a patch, which means rereading the surrounding code plus everything the agent has learned in the previous 4 steps. So it goes into the model carrying the accumulated context of the entire run so far. The other is a full verification pass, which reruns the suite from the top. Both of them are more expensive than the equivalent step in the earlier graph, and they are more expensive for the same reason. The context they drag along has grown. So cost is not a function of a node count. It grows faster than the node count because every decision is made against everything that came before it, and the pile keeps getting bigger. My question to you is, which run was your timeout sized for? Which one was your worker pool sized for? And when somebody priced the product, which one were they picturing? You had to pick, and the admission event made you pick before you knew. Which brings me to my argument. By the way, I like to do a lot of unpopular and hot takes. So feel free to just disagree with me at any point. But anyways, this brings me to my argument, which I actually wanted to make, and it is bigger than the fact that agents are unpredictable. A request is a wrong thing to price and a wrong thing to bound. A request works as a unit of accounting because of one property. The cost is knowable at the start. Take that away, and there is not a lot left to work with. You cannot charge it for, you cannot charge it for its honesty. You cannot limit it in any way that means anything. Again, going back to our previous two runs, if you would have said, hey, let's execute, let's make sure that the request one executes in like maybe 1 minute. What if a path had failed and it had to go beyond 1 minute? Or what if you were like, okay, this request should only cost maybe like $5, just throwing out a number there. What if, again, something failed and it had to make more number of runs? And what if, it went beyond the budget? Would you rather have your request fail? Well, what you want is the run and its budget. Something bounded that owns a body of work and holds state across the duration rather than an instant, and carries an allowance you set at the top. A token ceiling, a dollar ceiling, a wall clock ceiling. When the run exceeds, the run stops because the run is the only thing that the system can tell it exceeded. Again, may work in some cases, may not work in some cases. Um, Many platforms that I have seen do not give you this cleanly today. So the rest of this is the three problems that fall out and what you can do about each while the industry catches up. So you have one execution, three infrastructure problems, and they are separate enough that solving one does not get you to others. The execution graph asks what work exists. Compute asks what can run right now. And environment asks what can run safely. Context asks what has to persist. Most agent frameworks answer the first one thoroughly and then hand you the rest, which is fair enough. Since those three are infrastructure and frameworks, and since those three are infrastructure and frameworks are not infrastructure, basically. So let's look at the problem one, compute. Look at the state on this side. Every slot in the pool is occupied. Discovery tasks are sitting in the queue waiting, and there is not a traffic spike. Your request rate did not change. The same number of prompts came in, and they turned out to be bigger than the one before. So, why did your capacity plan not catch it? Because you forecast from an average, and an average is only a good summary of a distribution within a thin tail. Agent run cost does not have a thin tail. You can see why from the two runs a branch did not add a fixed amount. It multiplies what follows it, and the branch can contain another branch. That is a compounding process, and compounding processes do not produce a tidy bell curve around a mean. They produce a body of cheap runs and a small population of expensive ones, which puts you in a bad trade. Provision for the mean and you queue exactly what when the work matters the most. Provision for the worst and you pay for the ideal capacity nearly all the time. So, what would you pre-provision for this? So, rather, I would say, like, would you pre-provision for this? I would say no, because both answers are wrong. The answer is not a bigger pool. The answer is a pool without a fixed size. And something that you can do today before changing any of the infrastructure at all, I would say go look at your distribution. Most of you have the data already, but you've probably never plotted for it. Go ahead, pull your tokens, pull your toll calls, duration, and dollars per run, and look at the P99. Sorry, look at the P99 and 95 rather than mean. I think a lot of you will find a gap between your median run and the worst run is larger than anything your capacity plan accounts for. Let's sorry. Okay, yeah. Let's move on to the next one. This is a boundary case, and it's worth a minute because this is where your failure becomes invisible, and invisible failures are expensive kind. Let's say your model provider is degraded. The next step in the graph cannot run. So you have ready work sitting in your queue and a low active compute at the same time, which should feel wrong. And adding workers does nothing because more workers cannot unblock your dependency. Meanwhile, the run still owes an outcome to whoever has asked for it. Now, put a timeout on top of that. The timeout was sized for a normal request, so it fires partway through a legitimate run. The person who sends a request gets a response. It reads as a completion. It looks as if your agent got through the investigation, wrote a partial patch, and got cut off before verifying. And what surfaced on the upstream is a plausible summary of the work that did not finish. Because summarizing is one thing that these systems are reliably excellent at. Funny part, you've paid for all of it incidentally. Every token up to the cut is on the bill, and you have got nothing usable back. And the accounting probably recorded it as a success. So your error rate stays flat while your cost per useful outcome climbs, and those two numbers live in a different dashboard, which is how this can run for months, depending where you work and what you do, without anybody connecting them. So, two things for all the people who are in a similar space. You know, one, separate your deadline because per tool call timeout and per run budget are doing different jobs, and you probably have one number doing both badly. Make the runs completion state explicit and and basically make sure the machine is checkable so that a truncated run is distinguishable from a finished one without a human reading the prose and forming an impression about it. Now, this is something that gets skipped because it did not look like an infrastructure problem until you try running something. Scheduling a task is not same as giving it somewhere to run. Going back to our previous runs, in the patch step, our agent asked what it actually needed. A checked out repository, a shell, a Git package installs, and a process that can build the project and run the test suite and drive a browser. That is a machine, not a function invocation. And since the agent decided mid run that it needed to run tests, you could not have provisioned that machine at admission either. Again, same problem as compute, but different resource. The awkward part is that the requirement pulls against each other. It has to be isolated because the agent is writing the code and then executing the code it wrote. It has to be disposable because You will create a lot of them, and if they sit idle, then you are back to paying for a pool that you could not size. Third problem is the context, or whatever survives when the model forgets. There are three layers here that get conflated constantly, and pulling them apart is most of the work. Model context is working set for one call, what the model can see at the instant. Workflow state is the plan and the output and the status, what was decided and what came back. Execution state is files and processes and artifacts sitting on the disk somewhere. The thing I want you to take from this slide is the larger context window is not a system of record. It is a cache with an eviction policy you do not control, made out of a resource you are built by the token, which is worth sitting for a second because the knife fix, putting everything in the window, is the most expensive available way to store state. You're paying for model prices for something a database would hold for a rounding error. And it does not work anyway. When the run gets retried or resumed, the window is gone and the other two layers had to be still somewhere. Your agent plan only exists in the prompt, and what you are calling a retry is a fresh run that shares the instruction with the old one. It will make its own decisions, and you will pay for both sets of them. So, the state turns out to be a product decision as much as an engineering one. Three questions to draw the line with. The plan. What can be reconstructed? If you can build it cheaply from something you already have, do not store, most people would persist over here. The second one is evidence. What has to be durable? Anything a human will be asked to trust later. If your agent claims it verified a fix, the evidence of that verification needs to outlive the context window. Otherwise, the claim cannot be checked, and an unverifiable claim sitting in a deploy pipeline is worse than a no claim at all. Authority. What may continue without approval? People leave this one implicit, and it is the one that costs money, because the run that discovers more work is a run expanding its own scope, and a scope is a spend. Authority is also where your cost control lives, and I want to be blunt about it. Why? Per request rate limits do not bind agent workloads in a meaningful way. One admitted request can consume unbounded downstream resources, and your limiter counted it as one and moved on the half a second earlier. Per your billing request, it has the same hole from the other direction. You're charging a fixed amount for an event whose cost you never measured. So the concrete version, give every run a budget at the admission, token, tool calls, dollars, etc. Enforce it inside the run and not at the edge, because at the edge cannot see any of these. Rate limit on what gets consumed rather than what gets accepted. None of that requires any platform to ship anything, and you could probably do it this week. Two primitives. By the way, Sparsh, how are we doing on the time? I probably need a couple of more minutes.
We are a bit short on time. We have 1 minute in the session, but we can take a few more minutes to go. That's okay. A very interesting talk. Ojus, I don't want to interrupt you. Please continue.
Basically, two primitives, and it had like two jobs. And I'm showing them the map because these are two problems I just described. Workflows owns the execution order, so the graph and the state, and the dynamic compute and recovery. Sandboxes owns the environment, so isolation and file system and tools and lifecycle. Sandboxes, basically out of the three problems that we discussed, we at Render are solving two of them. One is the first problem with graph state, dynamic compute and recovery is being solved by workflows. the isolation file system tools and lifecycle is being solved by Sandboxes, but it's still in development. The third problem is something that I would ask you to solve. In the interest of time, I do not want to go over some of these, but I would highly recommend you to take a look at what durable workflows are and how you can use them to kind of like solve some of these, problems. Anyways, if you have more questions or if you want to explore how we are solving this problem, feel free to join our render Discord community. It's a Discord community of more than like 1,000 render developers. My team actively manages it. So if you have any questions, like you can feel free to kind of like reach out to me or anyone of us. And feel free to scan this link. It gives you $50 credit in render. So if you want to, like deploy your workloads on render, you can definitely use this link. I'm going to stay here for like maybe 30 seconds just to see like if you guys.
Thank you so much, Ojus. There are a lot many questions in the chat, but I think we are a bit on time. But very interesting topic. Thank you so much for putting these all thoughts into our mind, because I think we generally have not thought, like lot many people have not thought about how we can basically save the cost while agents are working in loop. There are also a ton of questions like how like if agent is running on loop, or if it has lost its context, or if it's at a stale state, how we can basically plan that ahead of time. But I will share all the questions with you later after this session, so that you can respond and maybe
And again, like if you guys have time, please check out what workflows are. They should be able to answer most of these questions for you.
Yep.
All right. Cool.
Awesome. I will also be pinning this QR code link in the chat. So please do scan this QR code and trying your workflow on render.
Wow, there are
And
like so many questions. I'm just seeing them right now.
yeah,
Yeah. Okay.
very
All right.
interesting. If you want to take one of them, if you find any one of them interesting, you can just
Absolutely. And
answer that.
again, these are very interesting questions. Please, I'm putting my email in the chat. Please reach out to me. I will try to answer most of these questions as possible. Let me see one question. Tasks. How do I validate agentic AI workflows? Um, so this is a very good question, and I think the answer to that is very broad. So it just depends, like what workflow am I optimizing for, I would say, and what the outcome is. Again, my hot take, it doesn't have to work with everyone, but I kind of decide to use frameworks for what I'm building for. Again, depends on what I'm building at the end of the day. Some of my favorite frameworks, I would say, is like Mastra. Take a look at it. They have like a good TypeScript SDK. It's open source. And most of the times I know what my input is, what my output is going to be. And then based on that, I try to kind of like, see what the outcome is. And again, use something which can make sure that your workflows run. So again, you can use like background jobs or retries or queues to make sure that your workflows succeed. Or again, like there are many open source or like paid tools available out there which promise you durable workflows. You can take a look at some of those as well.
Thank you so much, Ojus. Uh, I will be sharing all these questions with you over the chat. And meanwhile, if somebody wants to connect with you, I have also dropped your LinkedIn in the chat. So please do ping Ojus. He is pretty active there. So you can ping with your questions and we will help you respond to that. And we'll be also posting all the responses from Ojus on our blogs as well as YouTube videos that we'll be posting with this recording. So stay tuned, subscribe to TestMu YouTube channel so that you are getting all those responses. And thank you so much, Ojus, for sharing this point of view. Really enjoyed it. And I would like to thank everyone for joining and sharing your questions. And we'll see you in the next talk.
Yep.
Thank you, everyone.